So in the previous video, we spent quite a bit of time deriving certain key properties of the determinant. Now I want to kind of balance it out with a much shorter video where we just utilize these properties, right? So I have the first example written up, and let's see what we're given. So we're told that A and B are 3 by 3 matrices, and that the determinant of A is 2 and the determinant of B is -3, and we have four other determinants that we have to compute. And if you notice, if you look at the matrices whose determinants we have to compute, they all involve these operations that we've done with matrices. We have the product, we have a transpose, we have an inverse, and then a scalar multiplication all together there. And something similar here, but we have, it looks like we have a scalar multiplication and then the inverse of that entire thing, right? So let's go through and see how we would utilize the previously developed properties to answer each of these questions. Now, part A, this one is a direct application of one of our theorems, one of our properties, which states that the determinant of the product is equal to the product of the determinants. So the determinant of AB is equal to the determinant of A times the determinant of B. And since we're given those two numbers, all we have to do is multiply them, right? So even though we don't know what the specific matrices are, right, if we only need to work with their determinant, we can say that the determinant of AB is going to be 2 times -3, which is -6, right? So that's our first property there. The second question deals with two operations, scalar multiplication and the transpose. Now, for scalar multiplication, we have the ability to factor this constant outside the determinant. But the property says we have to know, for instance, how many rows we're going to factor this 2 out of. And that's why we need to know the dimension of the matrix. So because it's a 3 by 3 matrix, the property says that the one that deals with scalar multiplication says that the determinant of 2 times A transpose is equal to 2 to the third power, right? Again, we're factoring out a 2 from each of the 3 rows for a total of 2 times 2 times 2, and then we're left with the determinant of A transpose, right? And then, but we have a property that tells us how the determinant of the transpose is related to the determinant of the original matrix. And in fact, they're exactly the same. Taking the transpose has no effect on the determinant whatsoever. So 2 times, in fact, let me write it down like this, right? So we can see kind of symbolically how it breaks back down, right? So because the matrix is a 3 by 3, we have to raise this constant to the third power, and then we can multiply that by the determinant of A, because the determinant of A and the determinant of A transpose are the same. So we end up having 8 times 2, that's equal to 16, right? Next up, we have scalar multiplication, but now it's times an inverse. So we're going to have to do the same thing. We can factor out the 4, but then it becomes 4 to the third power, because again, we're working with a matrix that has 3 rows. They each get multiplied by 4, so they each have the effect of 4 times the determinant of the original, right? So this is 4 times 4 times 4, so it's 4 to the third power times the determinant of B inverse. The last property that we proved in the previous video was that as long as the determinant of the original matrix is not 0, So as long as the determinant of b is not 0, then we can find the determinant of the inverse of b by taking the reciprocal of the determinant of b. So it looks like this. So it's 4 to the third power times 1 over the determinant of b, right? And again, that's why we need this to be non-zero. And again, we know that it's non-zero because if the matrix, or we should say, since the determinant is not 0, then we know that the inverse exists, right? So we have 4 to the third power, that's 64, times, and then 1 over -3, so it looks like this. And then we can write that as -64 over 3. Right? And then finally, how do we do this one? Well, let's think about it. We have 4b in parentheses, and then we're taking the inverse of that. Well, through properties of exponents, we know that this is the determinant of 4 to the -1 times b to the -1, right? And again, this -1 is interpreted differently. This represents the reciprocal of 4. This represents the inverse of b, right? So let me write that before we apply our other properties. So this is 1/4 times b inverse. And then it's going to look very similar to this one. The only difference is now we're factoring out a 1/4 as opposed to a 4, right? So when we take out that 1/4, again, it has to be raised to whatever number represents the dimension of our matrix. In this case, it's 3. So it's 1/4 to the third power times the determinant of b inverse, and we know that the determinant of b inverse is 1 over the determinant of b. So what do we have here? We have 1 over 64 times 1 over -3, and then that gives us -1 over 192, right? So quite easily, once we know these two things, once we know the dimension of the matrices that are involved, and we know their individual determinants, we can find the determinant of many other matrices that are related to one or both of them, right? Okay, so a nice little example to start out with, and well, what are we going to end with? Because I did promise a short video. I just want to show you one of those examples of a determinant where you can tell just by looking at it without doing too much work. So I'm actually going to write down a 5x5 determinant. Right, so it's going to be 2, -1, 3, 1, 0, -5, 6, 1, 1, 2, 4, -3, 2, 8, 10, 6, oh, I said 6 and I wrote 3, so 6, -3, and then 9, and 3, and 0, and then 10, 1, -1, 0, 8, right? So here's our determinant. And just looking at it, man, this is going to be, if I had to use cofactor expansion, this would probably be the longest video ever, right, to compute this. And even if we tried to pick a, like column 5, for instance, it has a couple zeros in there, so we might want to start there, but it's still a 5x5. We would have to break this down into 5 4x4s, and then each 4x4 will get broken down to 4 3x3s, and then each 3x3 will get broken down to 3 2x2s. That is a lot of work. But it turns out I can tell just by looking at this closely that this determinant is 0. And this is why. Look at row 1 and look at row 4. They are scalar multiples. of each other. Row 4 is equal to 3 times row 1. And whenever you have that kind of relationship between your rows or columns, right, the determinant has to be equal to 0. So let's write it down to say this is equal to 0, right? And I encourage you, if you have a device or if you know of a website that you can go to compute a determinant, go ahead and put this in and see what you get. But it is going to be 0, and it's because row 1 is a constant or scalar multiple, right? Multiple of row 4. So no cofactors needed, not even the row operations needed, but it's just an astute eye to see, hey, look, if I take 3 times row 1, I'll get row 4. And we established a property that says if one row is a scalar multiple of another row, then the determinant has to be equal to 0, right? Easy solution, but takes a sharp eye. I know you have a sharp eye, so why don't you use that eye and maybe check out the next video. See you then.